Welcome to Lecture 11. Today we're going to be focusing on equilibrium for the combustion event and the types of fuels that we're going to use in our internal combustion engines. This is a long lecture. There's a lot I'm going to cover. A lot of it will be beyond what we're able to do in class time, but it is important to have these concepts in your mind as we go through it. So let's dive right into what we talked about last week, which was adiabatic flame temperature. And what I've plotted here is the actual adiabatic flame temperature for a number of different fuels in either air or pure oxygen. And this is plotted as a function of the equivalence ratio here. So on this left-hand side, this is your lean combustion, and on the right-hand side, this is rich combustion. Now, a couple of things to note here. First of all of these plots are assuming that the reactants, the fuel and air, are initially starting at 300 degrees. It's still very possible for us to get temperatures that are higher than this when we start the reactants at a higher temperature and higher pressure. Second, I before mentioned that the most complete combustion, thus the most efficient engine, tends to be slightly lean, a little before an equivalence ratio of 1. But that's not where we see the highest flame temperature, and that's okay. The reason is, on this left-hand side, we might get more complete combustion in this region, but there's extra air that's diluting that full combustion, and that's absorbing some of the energy and not allowing the temperature, the flame temperature, to be as high. Just to the right of 1, so a slightly rich combustion over in this area where we see this highest flame temperature, we might not be burning 100% of the fuel. We're burning most of it, but there's definitely no air. There's absolutely zero excess air to absorb that heat. So your highest possible flame temperature will be slightly rich combustion. Your most efficient engine is just slightly lean combustion. So another thing to note from this slide is that all of our sort of general hydrocarbons, everything from something as light as hydrogen to something as heavy as octane, when it's burned in air, all of these hydrocarbons, generally speaking, have flame temperatures in the same ballpark. They're not radically different by 20 or 30%. There is a significant difference, though, when you go to burn things in pure oxygen. So that nitrogen dilution has a big impact on the flame temperature. So that's just a thing to note, that if we're starting with room temperature gases, we're expecting basically everything to burn between 2100 and 2500 at stoichiometric conditions. Okay, why did the flame temperature not go to 5000 degrees? That's what we discussed in the last lecture. And we alluded to chemical equilibrium. And so in every reaction, there's some amount of entropy generation as you burn something. And at some point, it's a lower entropy position, meaning more organized, to have complete combustion than it would be to have partial combustion. So the second law is basically saying that entropy is always going to increase during a reaction, or during anything. The universe will continue to increase its entropy. And what that means for us is that we can use this principle of increasing entropy to define how far the reaction will proceed before it stops. So it wants to get to this point of maximum entropy generation. So the way we actually solve that is, rather than solving for entropy, we solve the inverse problem and we try to minimize the Gibbs free energy. So instead of trying to find the peak of that hill, which numerically is difficult because it's an unstable position, mathematically, if we find this minimum, it's helpful. We find just the gradient and we take a step in that direction until we fall into the bottom of the cup. So how is Gibbs related to entropy? Well, we have the principle that entropy always has to increase, and we have our first law, which is saying that the heat into a system minus the work out of a system is equal to the change in internal energy. Well, if we combine those two together, we get the Gibbs free energy. And you're actually subtracting this TDS term, so that's what changes the sign from a greater than or equal to a less than or equal to, and changes shape from a mountain to a cup. So this is our definition of Gibbs energy here on the left. It's the differential internal energy plus the flow work minus this temperature times ds term, which covers the entropy. So from these equations, we deduce that we're trying to find the point of minimum Gibbs energy, and that is where equilibrium will occur. Now, sometimes equilibrium might appear really close to the final products. It might look something like that. At very high temperatures, equilibrium is going to shift more towards 50-50. Or could actually, at very high temperatures, shift to the opposite, where you would have mostly reactants. They don't actually want to complete the combustion. So how do we actually solve for this? Why do we use equilibrium to solve for a combustion process? Well, previously we'd been doing something like hydrogen and oxygen burning to water. But now we're talking about having these species that are part of the incomplete combustion. So other things like hydrogen, unburned hydrogen, split monatomic hydrogen, hydroxyl, monatomic oxygen. How do we solve for this composition? We've only got two species in this case, hydrogen and oxygen, that we can use to balance the number of atoms, but we have several unknowns here. We would have 1, 2, 3, 4, 5, 6 unknowns in this place. So we're missing four equations to be able to solve this. And the way we're going to get that is from equilibrium reactants. So imagine I have some equilibrium reaction between oxygen and monatomic oxygen. I have some equilibrium reaction between water, hydrogen, and hydroxyl. I have a different equilibrium reaction between hydrogen, diatomic hydrogen, and monatomic hydrogen. And I'd probably need to get one more in there. I'm not sure what it would have to be, but I'd have to find one additional equation. Then I could balance these reactions, but that's not quite everything. And we'll come back to the answer of why that's not all after we talk about these equilibrium equations that we're going to pull in to solve. So we need 4 equilibrium equations. What are those? Well, what we're looking for is some constant that we can put in a table, or some constant we can measure experimentally and use to define equilibrium, so that if we experimentally did it under some conditions, hopefully that constant could still apply in other conditions. So the way we're going to get there is from this derivation of Gibbs function, and the nomenclature here, the bar is just representing that I did everything on a molar basis, but the derivation would still apply on a mass basis. So if we start from this definition of Gibbs energy, and we pull in a definition from an isothermal process for the entropy change, we can combine those two things to get the change in Gibbs free energy at constant temperature. So imagine we have the temperature defined that we're trying to find equilibrium at, and as a function of the species and the energy, the enthalpies, how do we find that shape that was a cup? The delta G is going to define how we find that minimum Gibbs energy. So we put those equations together and we get something else down here that's a function of temperature and pressure. And we're going to define this starred term, which is a reference standard Gibbs energy, and then we know that's going to be modified by this sort of gas term, which is RT, natural log of the pressure. So for each species, each molecule will have its own balance equation like this, and we're going to try and group things together and solve them so we can get a constant for each reaction. So let's start with sort of an idealized reaction where we have two reactants, A and B, and two products, C and D. Now these VA, VB, VC, VD, these are stoichiometric coefficients. These are the pre-multipliers that we're looking at. So I know this one that I'm showing you only has one reactant, but it'll simplify a little bit more, but the derivation will be for A, B, C, D. But I'll use the example of equilibrium between carbon dioxide, carbon monoxide, and oxygen. So in this case, A is carbon dioxide, VA is 1. There is no second reactant, so VB is 0. The first product is carbon monoxide. The second product is oxygen. So if we take the definition of each species Gibbs energy, and we balanced the Gibbs energy of the reaction, we would have the product C plus the product D minus the reactant A minus the reactant B. And we're doing the Gibbs energy of each of those. So now we're going to lump all the constant terms. So these starred terms at a given temperature are constant. So if I pull those all out here, I can get those lumped into a single term, which I'll call delta capital G star. And if I pull all of those to one side of the reaction, what I'm left with on the other side is this part that's RT, natural log of pressure. So with some tricks with natural logs, we can group those together. So on this left-hand side, I have all of these constants as a function of temperature, and on the right side, I have the part that's a function of temperature and pressure. So with the natural logs, when you add them, they're multiplying. When you subtract them, it's dividing. So what we get is this RT, natural log of the ratio of pressures, and it's going to be, because there's this negative sign here, normally we would do, that negative sign is going to drop out at this point, I believe. And what you're left with when you have it in positive terms, it's products over reactants. You might see this in other textbooks with a negative sign there, and it's reactants over products if there's a negative sign. Trick with natural logs is when you flip the fraction, it's the same as a negative outside the natural log. So now we want to use this equation that we have here. This change in Gibbs, standard Gibbs energy, is some function of temperature, and that's also a function of temperature and pressure. And we're going to try and find when the change in Gibbs goes to 0. So we're going to do that by defining this equilibrium constant. And this equilibrium constant is going to be equal to this ratio of pressures of the species. Now we can use this previous equation to get it in a couple different forms. So we'll define it this first way as the ratio of the pressures, but if I rearrange the previous form, I can actually get it as a function of the standard delta G, temperature, RU and T. So this time it's only a function of temperature. Here it's only a function of pressure. And then finally I can take this partial pressure equation and I can pull out the pressure so that now it's a ratio of the molar concentrations. So these are the mole fraction ratios multiplied by the total pressure of the gas and the number of moles total here. And then this delta V is just the difference here in these exponents VC, VD, VA, and VB. So delta V is the difference of the stoichiometric coefficients, products minus reactants. So what I want to hit on again here is that all three of these definitions of Kp are equivalent. And what we can do with this is, given some concentration of species, we can find the equilibrium constant. So we could run an experiment knowing the temperature, measure the species, and find this equilibrium constant and tabulate it as a function of temperature. Then when we're actually using this, I can know the temperature. I can, from the tables, I can look up the equilibrium constant, and then I can use that original definition to go back and solve for the partial pressures or the species using one of these other two equations. So that's the arrangement of the equilibrium constant. We'll get to some examples of how we use that, but that is where it's derived from. And the next step is, it's fairly straightforward when we're doing this for a single reaction like CO2 splitting into carbon monoxide and oxygen. But when we start to get systems of these reactions, multiple of these together, they all get embedded, and it's basically impossible to solve by hand. So we'll show you some tools for doing this. So when you have simultaneous reactions, you're going to use a different equilibrium reaction to add an equation to your system of equations until you have the correct number of equations as you do elements. If any species were to appear in two different equilibrium relations, so let's say we had one equilibrium between O2 and oxygen, and we had a different equilibrium reaction between CO2, CO, and oxygen. Those two are going to have to be solved simultaneously because this amount of oxygen will play a role in both reactions. In the end, what we're trying to do is minimize the Gibbs function. And if we want to know how many equilibrium reactions we need to come up with, we simply take the number of species in the products, the number of things we expect after the combustion has occurred, and we subtract how many different elements are in those. So if we were to have products of combustion with these four species, and in this case there's carbon and oxygen, so I have four components in my products, there's two elements, that means I'm going to need two equilibrium relations. So before we start with an example of burning hydrogen with oxygen, and we had all of these different species. There was 1, 2, 3, 4, 5, 6 species that we needed to balance. Since there's only hydrogen and oxygen, we need 4 equilibrium equations. Now we go and we get Kp for the 4 equilibrium reactions we pick, but there's a slight problem. When we find Kp, it's a function of temperature, and then we're going to need this pressure to be able to solve for the actual molar balances once we've found the Kp. So there's 2 new unknowns. How are we going to address those? Well, we're going to have to solve the system of equations for the mass balance, the equilibrium balance, at the same time as we do our first law energy balance, which tells us temperature, and at the same time as we do the ideal gas law on that temperature, and assuming we knew the volume, or if pressure was constant, we find the volume. Either way, we'll need the ideal gas law to get that pressure term correct. So now we have 8 unknowns, 8 equations, all being solved simultaneously. So typically, instead of setting these equations up as balanced stoichiometry, the way you count the number of oxygens on the left and the right, what we tend to do when we have this number of species is we're looking at ratios of the elements as our constraining equation. So instead of finding that the number of hydrogen atoms has to equal 6 in the balanced reaction, we're going to do everything in this mole ratio, because then we can get it in terms of the concentration terms. So these concentrations, XH2, XH2O, these are what we're actually solving for in those equilibrium reactions. If we go back with the definition of the equilibrium constant here, we're solving for these gas concentrations. So if I could get my stoichiometric balance in terms of those same variables, it makes the system of equations a little easier. And so what we have here is, if we have just hydrogen and oxygen, there's going to be one constant that is the ratio. So when I start, let's imagine I put my fuel and air inside that bomb calorimeter. They're closed off to the outside world. The mass is not going to change. No atoms are going to transmute into other elements. We're not doing that sort of alchemy. So we would have the same number of hydrogen and oxygen atoms after the combustion as before. So that ratio being constant is a constraint for my balanced system of equations, and it replaces the idea of knowing that I need 2 hydrogens and 3 oxygen atoms, if that's what I started with. The problem is that reduces the constraints by 1, because here I had 2 constants. Now there's just 1. So what is the makeup equation? The makeup equation is that since everything is now on a mole fraction basis, xi, we know that all of the mole fractions should add up to 1. So that is the final equation. So anytime you have converted the number of moles of each species into these ratios, you lose one equation, and the makeup equation is that the sum of the mole fractions is always equal to 1. So this constant isn't, it depends exactly on what your starting reactants are. So what is your fuel to air ratio? And how much hydrogen is in the fuel, how much oxygen is in the air. That is where that constant comes from. So it's very specific to your problem. It can't be tabulated the way the equilibrium constants can be. Okay, so let's walk back through that example of CO2 dissociating into carbon monoxide and oxygen. And this one's going to be fairly straightforward, since we have just 3 species. So if I set up the definition of the equilibrium constant here, is going to be the mole fraction of carbon monoxide to the stoichiometric coefficient in the balanced reaction, which is 1. The O2 mole fraction is going to be raised to the 0.5, because that's the stoichiometric coefficient in the balanced reaction. CO2 is going to be raised to the 1, because that's the stoichiometric coefficient in the balanced reaction. Now let me back up a moment here, and how can I have this balanced reaction when we're talking about burning some fuel and we haven't balanced the reaction yet? So how could I possibly set this up for a equilibrium reaction? Well, these equilibrium reactions are predefined reactions that are going to be perfectly balanced. You can't, if there's excess CO2 on this side, well, that can't really be. It's just going to be more CO2 disassociating. So there's no, and this isn't some fuel burning reaction that we're trying to balance. These are separate dissociation reactions, and they can be pre-balanced like this. They're always going to exist in this ratio if you were to start with pure CO2, heat it up, and let it dissociate. This is what it's going to do. So that's where these come from, and these can be tabulated, unlike our fuels, which might vary widely, these sort of remain, these reactions always exist. So water dissociating into hydrogen and oxygen, that's a known thing we can tabulate. So coming back to these exponents, you have CO to the 1 for its coefficient, O to the 0.5 for its coefficient, and CO2 to the 1 for its coefficient. Then you have the pressure that the reaction is occurring at, and that's then raised to that delta V, which is the products minus reactant coefficient. So I've got 1 mole plus a half a mole minus 1 mole. And so that's going to raise this to the 0.5. So that's one side of the equation for the equilibrium constant. The other side is I'm going to find the equilibrium constant for the reaction as this fraction with exponents of the individual equilibrium constants. So CO has its own tabulated constants, O2 has its own tabulated constants, and CO2 has its own tabulated constants. So I can pull those from a table, and I'll show you that table in Excel in a moment, and raise them to the same exponents as the mole fractions, and I get the equilibrium constant for this reaction of disassociating carbon dioxide into CO and oxygen. So the way these problems work out is I start on this right side here. I set up the balanced equation, I pull these constants from the table with the correct exponents, and I get this equilibrium constant. Now I have that this constant is equal to this function of the mole concentrations. And I'll do to that, I need to have that the sum of the mole fractions is equal to 1, and I need the mole fraction of carbon and oxygen I started with. So if I happen to start with 1 CO2, I have 1 carbon and 2 oxygens. Let's imagine in this case I started with 3 oxygens for every carbon, so I didn't start with all CO2. I started with some balance. Maybe it was all CO and oxygen. Whatever gave me a carbon to oxygen ratio of 1 to 3. So with these 3 equations solved simultaneously, I can find the equilibrium products of this dissociation reaction. And at 2500 degrees Kelvin, I've pulled these constants out of the table, 0.044 for carbon monoxide, 1.22 for CO2. And at 2500 degrees and 10 atmospheres, I get something that's 64% CO2, 33% oxygen, and about a little more than 1% CO. If instead I decide to leave it at the same pressure and I pulled the constants at 1000 degrees instead of 2500 degrees, I have almost complete CO2 and oxygen and no carbon monoxide dissociation. So lower temperatures tend to limit dissociation. A higher temperature here at 2500 degrees, I'm going to have more dissociation than I will at 1000 degrees. Pressure in this case is going to drive things the other way. If I have high pressure, I'm going to squeeze these 1.5 molecules back into 1 molecule due to Le Chatelier's principle. So at the same 2500 degrees and 1 atmosphere, so I'm lowering the pressure, which is going to allow more dissociation. I'm going to get almost 4% carbon monoxide when I lower the pressure at the same temperature. So here's 2500 degrees and 10 atmospheres. Here's 2500 degrees and 1 atmosphere. Lower pressure allows more dissociation. Higher pressure will squeeze these back together and result in less CO. So combustion equilibrium for the sorts of things that we're going to be burning in our engine. Most of the time, what we've been focused on so far is having carbon dioxide, water, and nitrogen, and maybe some leftover oxygen in the products. In reality, we're also going to have some carbon monoxide, some hydroxyl, some hydrogen, oxygen, and nitrous oxide. This is the one that we're really concerned about because that's a bit of a poison. So one of the issues with having these extra species is that the ratio of specific heats is much lower with these extra dissociated species because they have much smaller, they're monatomics, diatomics rather than triatomics, so their specific heat ratio is generally lower. And that's going to affect the way we've been calculating the isentropic expansion. We've been assuming a constant specific heat ratio for the compression of the reactants as well as the expansion of the products. But in reality, we're going to have a much lower specific heat ratio during the expansion process. Now, I'm talking about nitrous oxide being one of the critical issues, and carbon monoxide is also a poison that we want to avoid. When we're at 2500 or 3000 degrees Kelvin, there's going to be significant amounts of these on the order of 5%. And what we want these to be down in the part per million, single digit part per million range is where we'd like them because they are such poisons. So how do we get rid of them? Well, equilibrium at 3000 degrees says there's lots of these carbon monoxides and nitrous oxides. But at 700 or 800 degrees, there's almost none. And that's what I was showing you back here on this last slide. At 1000 degrees, there's basically no carbon monoxide, whereas at 2500 degrees, there's a significant amount. So what is happening during the expansion as it cools, as we take work out of that fluid, the equilibrium is going to change. So once the combustion occurs, it goes towards equilibrium, but then it doesn't stop yet. As it cools, that equilibrium moves and these reactions finish their combustion a little bit farther. So that the nitrous oxides and CO will recombine into CO2 and then nitrogen during the expansion. But this is where we get into the kinetic problem. So equilibrium is one thing, but it takes some finite amount of time to get there. And at high temperatures, things happen really, really fast. So we can assume that the combustion immediately goes to equilibrium. As the temperature drops, things go slower and slower. So it starts to shift to less carbon monoxide and less nitrous oxide, but then that shifting slows down until it essentially freezes. So at some temperature, maybe 1500 degrees, maybe 1800 degrees, they basically get stuck at that equilibrium. So even when the products finish the expansion and they're down to 900 or 800 Kelvin, they might still be in the equilibrium ratios from 1800 degrees Kelvin. And that's the main hurdle of designing engines today, to try and facilitate that complete conversion of nitrous oxides and CO. So this is going back to that equilibrium constant. I'm going to show you an example here, and it's going to be the same example. I'm just going to pull up the Excel sheet to show you where these numbers came from. So an example question I can give you is find the equilibrium constant for this reaction of carbon dioxide dissociating into carbon monoxide and oxygen. And the way you're going to do that is you'll write out this balanced equation, and then you'll put it into this fractional form where you've taken the coefficients of your balanced reaction here and made them exponents. And then I'm going to go over to this Excel sheet, which I will post on our Blackboard, and find those species. So I have carbon monoxide here in column B, CO2 is in D, and we are looking for oxygen, which is here in C. And what you'll see is that each element in its standard form has a predefined equilibrium constant of 1, and everything else is relative to that. So diatomic oxygen always has an equilibrium constant of 1, pure carbon 1, diatomic nitrogen 1, diatomic hydrogen 1, and everything else will be relative based to that. So if we were trying to do this at 2500 degrees Kelvin, I'm going to come down here to 2500 degrees Kelvin and pull off these three terms. So we have 0.044 and then we have 1.22, and that's what we put into this balanced reaction here. So we had 0.0444 for the carbon monoxide, and 1.2 for the carbon dioxide, and 1 for the oxygen. And then it's just a matter of solving it with the exponents. And for this reaction at 2500 degrees, we get an equilibrium constant of 0.0364. So now I want to talk about what happens to this equilibrium constant. It's influenced by a number of things. It's influenced by the balanced reaction, it's influenced by temperature, it's influenced by pressure. So let's start by talking about how it is influenced by temperature. Generally speaking, at higher temperatures, you're going to have more dissociation. So when you talk about a reaction, here I'm showing it in reverse, carbon plus oxygen to CO2. At low temperatures, equilibrium is going to send it all the way to CO2. So it's going to be a very high equilibrium constant for this reaction in the direction from carbon and oxygen to CO2. As you go to higher and higher temperatures, you're going to have more of these reactants left over, so it's going to be a smaller number. The other point here is I want to make is that this equilibrium constant depends on temperature, not pressure, not the species that don't participate in the reaction. So if I have a reaction of hydrogen and oxygen burning or becoming water burning, the equilibrium constant for a given temperature, let's say 1000 degrees, is going to be the same at 1 atmosphere as it is at 5 atmospheres. Now if I have the same amount of hydrogen and oxygen and I add some inert nitrogen that doesn't participate, it just moves over here to the product side without becoming part of the water, the equilibrium constant for the reaction of hydrogen and oxygen to water remains the same, even if there's extra species, even if the pressure changes. And then finally, if I have extra oxygen, the same amount of hydrogen but extra oxygen, it's still going to go to water, and now there's going to be some leftover oxygen after we're done with that. This excess of any single reactant also does not influence the equilibrium constant. So for all four of these, the equilibrium constant is the same. It's not a function of the pressure. It's not a function of having some inert species, and it's not a function of the original ratio of your reactants. Now to clarify, the equilibrium constant is not a function of pressure, but the equilibrium concentrations will be. The constant is immune to that, even though when you do the mole balance of the x's, then it has the partial pressures in there. So even if the equilibrium constant is the same between these first two, you might have different equilibrium concentrations at those different pressures. Okay, what is the impact of pressure? I'm saying this again. Equilibrium constant is not a function of pressure, but the equilibrium species are a function of pressure, right there. So we can find this equilibrium constant purely as a function of temperature and then solve for these species as a function of pressure. Can't stress that one enough. Equilibrium constant is a function of temperature, but not pressure. The equilibrium species are a function of pressure. So what about the reverse reaction? I showed you a moment ago we had CO2 dissociating one way, we had oxygen, carbon combining the CO2 the other way. They're both defined by the same equilibrium constant. It's just that when you reverse the reaction, you inverse the equilibrium constant. So if I've defined my equilibrium reaction as hydrogen and oxygen becoming water, and I find the equilibrium constant from the table, the way I do that, I'd go to the Excel sheet. I'd pull off the values for hydrogen, water, and oxygen at whatever temperature I'm interested in, and I calculate the Kp, I'm going to find this number. It's a pretty big number, 11 trillion. If I define this equation in the reverse direction, what's going to happen is it's just 1 over 11 trillion, and you get this very, very small number. So that's how they're related when you switch the order. What this means, again, I want to point out, is here I have a fuel and an oxidant that I know at this temperature should burn to produce water. And so I have a very large equilibrium constant, and that means it's going to go most of the way in this forward direction. A very small equilibrium constant means that it's going to go in the opposite direction. So if it's 1, it's pretty balanced. If it's less than 1, and especially if it's this far below 1, it's almost always going to go completely in the reverse direction. A very large number means it goes almost completely in the forward direction. And you can see that from the fraction here of partial pressures, that if I have products over reactants, in this case, for the first example, I would just have water in the top, and I would have the leftover hydrogen and oxygen in the bottom. We know it's going to be almost all water and very little hydrogen and oxygen, so that's why it's a fraction that's 11 trillion. And if I flip the order of things, so I reverse the reaction, and I have hydrogen and oxygen on the top over water, I know that the equilibrium concentrations are the same. Whether I write the equation in the forward direction or the backwards direction, the final products are always going to be the same. But now I have a really big number on the bottom and a very small number on the top. That gives me the very small equilibrium constant. So how do I know to write the equilibrium as 1 carbon dioxide to 1 carbon monoxide plus half an oxygen versus doubling everything up so that I have nice even stoichiometric coefficients? Well, if I look at the balanced mole fractions here in the definition of the equilibrium constant, I can see I've been using these stoichiometric coefficients as the exponents, and I do the same thing and I double each of those exponents. Well, that's going to work out to just being the original equilibrium constant squared. So this is important. You can write your equilibrium reaction this way rather than this way, but if you're looking up tables and you find an equilibrium constant for this reaction, you're just going to have to square it to do this reaction. Backing up a moment, let me define this as sometimes we can calculate this equilibrium constant from the equilibrium values for the individual species. And that works either way. Nothing would change in calculating in that process. But the K that you've found is now specifically for this equation that's 2 carbon monoxides and 1 oxygen to 2 CO2. So sometimes we might find tables of equilibrium constants for the reaction so that we don't have to do this step and we can pull the equilibrium constant right from the table. Then it's really important to note, as they define that table, is it this reaction or is it this reaction? So again, doubling the exponents to balance your reaction is the same as squaring the equilibrium constant. So that's the takeaway from this slide. All right, keep moving on. The completeness of the reaction, I hit on this already. This is just to say that the larger the number, the more the reaction moves in the forward direction. So in this example of hydrogen dissociating into individual hydrogen atoms, the higher temperature you go, the larger the equilibrium constant gets, and you get more and more individual hydrogen versus diatomic hydrogen. So at 1,000 degrees, you have basically 0 hydrogen on its own in the mixture. At 2,000 degrees, you have 0.1% of hydrogen, and it's 99.8% diatomic hydrogen. At 3,000 degrees, you're at 14% of the individual hydrogens, so somewhere in that 3,500 degree range, it's probably 50-50. 4,000 degrees, you're mostly now individual hydrogen atoms, and it just keeps breaking down after that. Okay, so briefly for a moment, I want to talk again about the difference between equilibrium and kinetics. So the equilibrium calculations that we can do, they provide information on the final composition of a reaction if given infinite time. Now in some reactions at high temperature, infinite time doesn't actually take all that long because the kinetics are so fast, it's going to get to equilibrium perhaps in a matter of milliseconds or less. At low temperature, it could take years or millennia to get to equilibrium. Catalysts can speed up reactions at low temperature. So that's an entire field of study, is to speed up kinetics and get them towards equilibrium at conditions where you prefer the equilibrium. So let's say you want to make ammonia. To get that to happen, you would need high temperature because you need the nitrogen and hydrogen to get together, and the hardest part is breaking the triple bond of nitrogen and nitrogen. But at very high temperatures, equilibrium says that there's only going to be like 2% ammonia. So you need the temperature to be lower, let's say 1,000 degrees Kelvin, where you might get 15% or 20% ammonia in the products, but it would take a lifetime for that reaction to occur. So we put an iron-based catalyst in the mix, and it allows the kinetics to speed up at that lower temperature. So this is a lot of chemistry, and a lot of producing fuels is finding the balance between the equilibrium conditions you want for the product that you're trying to produce, and finding the catalyst that speeds you up getting there at the conditions that are ripe. So let's conclude this section on equilibrium, and then we'll move on to fuels. But I want to conclude this with an example more relevant to the types of things we're doing in our internal combustion engines. So let's imagine we're burning N-octane at 2 megapascals in dry air with 150% theoretical air. So if I set up my balance reaction, it's dry air, so I've only got oxygen and nitrogen, and I'm burning N-octane here, C8H18. But instead of just considering these first 4 products that we've been doing, I'm going to add in a few more things that I think might show up in the products. So how many equations do I have here? Well, there's 11 unknowns when I count A through K, but A I can get ahead of time because I know from stoichiometry of complete combustion. So if I did this with complete combustion, I could find the A for 150% theoretical error. So A is sort of taken care of beforehand, and what I'm left with now is I have 1, 2, 3, 4, 5, 6 new coefficients I need to find as B, C, D, and E change. So there's 10 coefficients here on the product side, and we need to find all of those simultaneously. I still only have 4 species: carbon, hydrogen, oxygen, nitrogen. So I'm going to need 6 equilibrium reactions to do this. So there is no unique set of equilibrium reactions. There's a number of ways this can be done, but there's some rules for defining a minimum set that you need. Each species of products, so each of these things, these are my species in the products, each of those has to appear in at least one equilibrium reaction. And then each equilibrium reaction has to have exactly 1 degree of freedom. So I can't put I can't have water and CO2 splitting into hydrogen, carbon monoxide, and oxygen. That would have too many degrees of freedom. So each of these reactions really just is splitting one thing. So here's an example set that works for a lot of hydrocarbon combustion, and basically anytime we're burning something to this list of products, then this list of equilibrium constraints would apply, but it's not unique. There are other sets that would work just as well. So I'm going to look at dissociation of carbon dioxide, dissociation of water, dissociation of hydrogen, dissociation of oxygen, another balanced reaction with water, but this time pulling in hydroxyl instead of oxygen, and then finally nitrogen and oxygen going to NO. So I mean there are other ways to get this hydroxyl. You could do an equilibrium reaction between OH, oxygen, and hydrogen, and that might substitute in here and change this set. But this is a functional set that works fairly well. And so for each one of these equilibrium reactions, you have to set up the relationship between pressure and the mole fractions, and then set up the same thing with the equilibrium constants for each species. These I'd go get from the Excel table. So the right-hand side of each of these I would know. The left-hand side is a function of these species and the pressure. And then I need that the sum of the species is equal to 1. And then I need all of those fractions of what I started with. So if I started with, in this example, 8 carbons relative to some other number of oxygens, 18 hydrogens relative to some number of hydrogens or oxygens, and then some amount of oxygen relative to nitrogen. That'll give me my 3 fractions. So that's what I'm showing here is we'd get these fractions of the reactant atoms, and I've given it in terms of the X, Y, and Z that we've been using to define the fuel species. And so that'll play out. This only applies for dry air, but now we have these 3 equations, the sum equation, and you can see those 4 plus these 6 are all now functions of the mole fractions and pressure. So I have ideal gas law to handle pressure, and I have the energy equation to find temperature. So that would be the set of equations. And if I wanted to solve by hand, the way I'm going to do that is not do that. So let me show you an example of how we can use one of these online tools to solve for equilibrium. So I'm gonna, my preference is this one here from Colorado State. So let me pull that up and show you how I would use that. So this is the web page that pulls up. It's a chemical equilibrium calculation. Let's say I have fuel starting at 900 Kelvin, and let's say that it's at 10 atmospheres. And I'm just going to estimate that it's somewhere around 2500 degrees when it's done, and let's say it is, let's do constant pressure combustion. This is just a guess. These second two boxes, it's going to solve for those. It just prefers some sort of a decent initial guess. It'll happen faster the closer your guess is. So if I wanted to do constant pressure combustion, I'm going to choose this constant pressure and enthalpy. That constant enthalpy means there's no heat loss to any of the surroundings. If I instead wanted to do constant volume combustion, I'd come down here and pick constant volume and enthalpy. This sheet's a little weird. It shows that you can select two with check marks, but it only works by checking one. So you have to make sure you've only checked one here. So now let me go ahead and put in the elements I have. I know I have carbon, I know I have hydrogen, I know I have oxygen, and I know I have nitrogen. And then on the reactant side, so the fuel, I'm going to say I have C8, H18, and I'm going to have 1 mole of that. And then I know I'm going to have oxygen. And if I did the stoichiometry to find that coefficient A, it worked out to be, I think, 18.75. And if you do that as there's 8 moles to balance the carbon, and then 18 divided by 4 is going to give you 4.5. So stoichiometric combustion would be 12.5. And then we wanted it at 150% of theoretical air, so 12.5 times 1.5 gives us that 18.75. And then I have the nitrogen that's in the air, and if I do that A, 18.75 times 3.76, I get 70.5 moles of nitrogen. So these were my reactants in the balance reaction that I was looking at here. So in this balance reaction, I found A to be 18.75, and I'm specifying what the reactant side is. Now I need to just identify what products I'm interested in. So if I go down to the next section here, additional species. So I need to note any species that aren't in the products that could be in the reactants. So I'm definitely going to have CO2, definitely going to have some water, I'm going to have some carbon monoxide, I'm going to have some nitrous oxide, I'm going to have some hydroxyl, hydrogen, individual oxygen, and I think I'm missing one. CO2, nitrogen, hydrogen. Okay, I'm missing H2. All right, so now I've got my 8 species here plus these 2 species, so those are the 10 species in my products, and all I have to do now is come to the bottom and hit calculate, and it'll open this up. And you can see here what it's calculated is we're staying at constant pressure of 10 atmospheres. Temperature has increased from 900 Kelvin to, it looks like, 2285 Kelvin. So there's our adiabatic flame temperature right there. That is the equilibrium temperature. Because I picked constant pressure combustion, the volume has increased. So if I were doing a diesel cycle, this ratio of volumes here would be equal to the ratio of the cutoff ratio. Enthalpy has remained the same because that's what I selected. And down here I get to see what the equilibrium products are. So it looks like I've got about 6% oxygen, 73% nitrogen, 12% CO2, 6% water, 0.1% carbon monoxide, about almost 1% nitrous oxide. So these extra species here, you can see they're smaller than CO2 and water, but they're not so small as to be negligible. If I go back instead, and let me try this again, but instead of doing constant enthalpy combustion, meaning adiabatic, let's say I burned it and then cooled it all the way back down. So let's say constant pressure and temperature. So I combusted it and I cooled it back down. Constant pressure and temperature is what I'm selecting, and I calculate equilibrium at 900 degrees. What you'll see is now these extra species, the NO, the OH, hydrogen, now they're really small and basically negligible. So at 900 degrees, we assume complete combustion. But at 2500 degrees or 2250, wherever it was before, we can't neglect these extra species as easily. So that's how you use the online tool. And that concludes the part of my talk that's on equilibrium. The last part of this talk is about fuels themselves. So the fuels that we're burning, so far we've been balancing these reactions for a particular fuel, maybe a combination of these two. But those aren't the fuels we use in our vehicles. And so I want to explain the differences here. Your alkanes are your basic hydrocarbon fuels that are the closest to a biofuel. So this is what plants grow, is carbon with lots of hydrogen. And then over time, an underground high pressure and equilibrium breaks these down into things with more carbon and less hydrogen. So in your fossil fuels, you start to get more of these complex carbon arrangements that aren't long chain hydrocarbons. So as things break down underground over thousands of years, you get more of these benzenes, toluene, naphthalene, these ring structure of carbons. So this ring is representing 6 carbons around in a circle, all bonded to each other, rather than a single long chain of carbons. So you get a bit more carbon relative to hydrogen because carbon is bonding to itself more often in these arrangements. So you get a denser fuel that way. Alcohols are very similar to the hydrocarbons. It's just one place that was bonding to a hydrogen is now bonding to an OH group. So methanol looks just like methane, but with one OH instead of just an H right here. And ethane, which was 2 carbons with 6 hydrogens, now instead of having a hydrogen right here, has an OH group. So those are the alcohols. Okay, there are some fuels we talk about that are non-hydrocarbons. We can talk about pure hydrogen, and this is what fuels fuel cell vehicles. You can also burn hydrogen in some engines. Rotary engines are pretty good for this. It is clean combustion. You're not going to produce as much nitrous oxide, but it's even cleaner if you electrochemically use it rather than combustion. The problem is it's low density. Even if you pressurize it to 750 atmospheres, you're still, or sorry, 750 750 atmospheres is the high pressure rating of most of the hydrogen tanks. It's still, you need a tank that's 4 times as big as your gas tank. The safety is actually really high. People worry about hydrogen as a fuel. It's because they see the Hindenburg explosion. In reality, it's very difficult to ignite hydrogen when it's under pressure, because as soon as you puncture that tank, it's going to be going supersonic. out of that tank and dispersing immediately into the atmosphere, and it'll be very hard to ignite, unlike gasoline vapors. It's also a rather difficult flame speed or flame to burn. It's good in an internal combustion reciprocating engine, like we've been talking about it, because it's in an enclosed space. It has a very high flame speed, but if you try to burn it in a turbine, it's quite difficult. Ammonia is an alternative fuel that gets bandied about a bit. We know how to make ammonia. We make a lot of it in this country for fertilizer. It also doesn't release any CO2 because there's no carbon in this fuel. We can make it at a price equivalent to about $1.60 of gasoline. The problem is ammonia is an irritant. You huff on that, you're going to kill brain cells. You can even die from it. So it's not a fuel people like, but it is a valid alternative. We can produce it from all sorts of sources very effectively. Hydrogen sulfide. This one's a bit more exotic. It also does not produce any CO2, and we can make it really easy. There's a lot of organisms, microorganisms, that produce this all on their own. So it's something we can make out of biofuels really quickly. The problem really here is the sulfur dioxide is nasty stuff. It's poisonous. It smells like rotten eggs because of the sulfur. So not a fuel choice that we're going to go with anytime soon. There are some other options. They also have their own drawbacks, but I won't get into them. Biofuels are the main alternative to the fuels we use today. And you start with something that's simply vegetable oil or animal fat. These are the original biofuels you can get from cooking oils from restaurants. And when you want to break this biodiesel down, convert that vegetable oil and animal fat into a biodiesel, you do something called transesterification. And you're going to have one large molecule that's a triglyceride, and it's a big, long hydrocarbon chain all wrapped around on itself. And what you're going to do is you're going to heat it up, and you're going to break it down into 3 separate long hydrocarbon chains. So under the right equilibrium conditions and with the right catalyst, this is what happens. So one triglyceride plus some alcohol will give you 3 molecules of biofuel and some glycerol, some really heavy stuff, which we can use for other things. We use it for soap and just all sorts of beauty products. So this process of making biodiesel from vegetable oil gives us a fuel and a really high quality product that we have a lot of uses for. The second generation of biofuels is the fermented food crop. So if you, instead of starting from an oil like vegetable oil, you start straight from the corn or sugar cane, you grind it up and you brew it the way you would brew beer or vodka. You add yeast, you add a bit of ammonia, and it ferments. And the product is probably about 20 proof from the fermenting, just like if you were making beer or wine. That's about the max proof you can get from fermentation. So at that point you strain out all the organisms that are doing the fermenting, and you keep distilling the water out of it until you get to something that's basically what might be termed grain alcohol. It's just rubbing alcohol. It's pure alcohol, 200 proof, not something you're going to drink. The next generation of biofuels is, instead of using these high sugar crops such as corn and sugarcane, you're using the stalks of the corn or sugarcane, or you're using trees. Problem is, it's a lot harder to ferment those. They're harder to break down. So you have to put a lot of energy in to get it from this biomass or woody crop into something that can be then fermented. Algae biofuels are a whole different process that I won't get into now. So, coming back full circle to the fuels we actually use today. All of the fuels we use today are blended fuels. There's no single molecule. It's not C8H18. It's, even though the fuel has an octane rating, it's not that. It's not C4H10. It is a mixture of these things, and we don't care about the properties of the individual molecules. What we care about is their aggregate properties. So the things we really want is that we care about our mixed fuel is the flash point. We don't want it to be flammable at room temperature, so we want to have heavy enough molecules in there that the flash point is high enough to be considered safe, but not so high that it's difficult to combust. We need a distillation curve, so we want to evaporate those droplets of liquid gasoline into the air even when the engine's cold. So when the engine's hot, sure, all of that liquid is very quickly going to evaporate and become a perfect mixture of fuel and air that we can burn. But when the engine's just starting up, just turning over, and it's really cold, we need some of the really volatile, lightweight hydrocarbons that evaporate at really low temperatures, so that they're going to evaporate as soon as they get into the engine, even when the engine's cold. And those will burn first, and it'll be really inefficient combustion at first, and then as the engine heats up, it'll be able to evaporate the rest of the fuel as well. We need certain amounts of paraffins versus olefins versus aromatics and alcohols to get these things, the correct flash point distillation curve. We also care about the impurities. We want to minimize the sulfur in our fuels, and we need some measure of how well it's going to burn. And so for us, we're going to use the octane number, and we'll get to some examples of that later. But these are the things that we actually care about measuring in our blended fuels as a combined property rather than of the individual fuel hydrocarbon molecules. So quick example here, if I wanted to compare gasoline to diesel, and we've done an example like this in the first week, how big would your tank need to be to have the same 400-mile range? So if a gasoline car is burning a tenth of a liter per mile, it's going to need a 40-liter tank. The energy content of gasoline from this previous slide here, if I look at the energy content on a volume basis of gasoline and diesel, that's what I'm using in this example. So the energy content is 1.27 million kilojoules. The equivalent diesel of that energy divided by the energy density of diesel is 35 liters. So a 40-liter gasoline tank holds the same energy as a 35.5-liter diesel tank. We've done these examples before, but this was just another place to look at that. So I mentioned the evaporation of the fuel as a function of temperature. So we need some mixture of the high volatile aromatics to the low volatile heavy hydrocarbons. The small weight stuff is going to be the most volatile, and we need some amount of those. Traditionally, we define this vaporization curve with 3 temperatures. So given the mix of the fuel, some percentage of the fuel is going to evaporate at different temperatures. So what this is showing on the bottom axis is what percent of the fuel is evaporated, and on this axis it's the temperature. So for this particular fuel, at 57 degrees, 10% of the fuel will evaporate. At 81 degrees, 50% of the fuel will evaporate, and at 103 degrees, 90% of the fuel will evaporate. So So those are the three numbers we use to characterize the volatility of a fuel. So we have the T1 when 10% of the fuel is vaporized, T2 when 50% is vaporized, T3 is 90% vaporized. Now sometimes on the news you might hear that gas stations are shifting to winter blends. What do we mean by that? Well, in the winter they want things to evaporate at a slightly lower temperature because your engine is going to be starting even colder than normal. So they're going to start with even lighter fuels that perhaps do something like this. The T1, T2, and T3 are all going to be about 5 degrees lower. So you will have evaporated 10% of your fuel at a lower temperature. So that's what we mean by winter blend. And all you're doing is you're changing the ratio of some alkane to alkylenes, or reducing the toluene in the fuel to get these vapor points. And the convenient factor is, since all of these fuels generally, the molecules have generally the same energy on a mass and a volume basis, it doesn't change the energy density of the fuel all that much. Though it is true, a winter fuel for a gallon will contain slightly more energy because you've gone to some of these more volatile compounds in it. Okay, so a typical composition, just as a point of reference, the C number here is how many carbons the molecule has. So about the majority of it is going to be in this region here. You've got paraffins with fairly low carbon numbers, 5 or 6, and then you get a significant amount of heavy aromatics. So these are the volatile compounds that you add in the winter to reduce the evaporation temperature, and then these are the lightweight, easy to manufacture from anything fuels. But it's a mixture of a whole lot of things, and they can dial in all of these based at the refineries. This is what the refineries are focused on producing. And they produce all sorts of different grades of fuel for different applications. So let's just compare Jet A, diesel, and gasoline for their slightly different applications. They all basically have the same energy. So that isn't what matters when we're creating the fuel. What matters is the flash point. So diesel takes a long time to get warming up, and that's why the diesel trucks take a long time to get warming up and operating rate. So that they have a very high flash point. Gasoline, we want to turn on that engine and go. It has a very, very low flash point. Jet engines, well, they're on jets. They know they can do a whole pre-flight procedure and get it warmed up. They've got a very long mission profile, so it's okay if it takes a while for that engine to get warmed up. Vapor pressure is very low for the jet engines. They do not they don't mind so much if you smell jet fuel. You go to the airport, everyone smells jet fuel. Same idea for diesel. You smell diesel wherever you go, but you don't smell gasoline as much. And that's because on cool days it's just not going to evaporate really at all. Freezing point. This is a target for all of these fuels. They want to be able to work on a -40 degree day. You might go up to Alaska. You'll get special fuels that have more alcohol or just pure vodka in there to lower that freezing point even farther. The auto ignition temperature is another key difference. Gasoline, we do not want them to auto ignite, so we'd like a high auto ignition temperature. Diesel engines, we are trying to auto ignite, so we generally want it below the temperature we're going to burn things at. And jet fuel, they want to burn that really easily, so it generally has a low auto ignition temperature. The density is more a product of tailoring these other attributes, but they generally fall in the same range, gasoline being the lightest and lowest density. The other fuels are denser. Another table, again detailing how different the fuels are and how their properties differ. This just bringing in, instead of just gasoline and diesel, here I'm also looking at biofuels, your ethanol, hydrogen, biodiesel, and propane, how they have these properties as well, even though they're not typically used in our internal combustion engines. So what doesn't distinguish one fuel from another? Energy content. I don't care, they all tended to have about 43,000 kilojoules per kilogram. What distinguishes the fuels is, for gasoline, you want a low distillation point, you need it to be easy to vaporize. You want a high octane number because you don't want it to combust before you want it to combust. So that's why we put ethanol into our gasoline, is to raise that octane number. Diesel number, we want a high distillation point. We want it to be very stable. We don't want it to boil off out of our tank. So it's hard to vaporize, but we want a low octane number because we want it to burn really quickly once it's injected to our engine. Jet fuel, medium distillation point, needs a very low freezing temperature because they're up at high altitude where it's really cold. So that concludes my talk on fuels and equilibrium today, both very important topics, and we'll spend some more time on these in class. Thanks for listening.